What if people living 1,000 years ago knew things about the universe that still hold true today? What if their ideas about the stars, planets, and the very structure of space were not as uninformed as some might assume? What hidden truths did they uncover between 500 AD and 1500 AD, peering up at the night sky? Number 12. The Earth's spherical shape. For centuries, long before ships sailed around the entire globe, scholars in the medieval period held a belief about the Earth's shape that might seem obvious now, but was a significant insight then. Many people might picture medieval times as a period where everyone thought the Earth was flat, a giant dinner plate floating through space. However, this popular image misses a crucial detail. Educated people, astronomers, and philosophers across different cultures widely accepted that the Earth was a sphere. This idea was not new to the medieval era. It had roots in ancient Greek thought, but it was preserved, developed, and taught throughout the Middle Ages in various centers of learning. Evidence for a spherical Earth was found in simple, everyday observations. When ships sailed away from a port, observers on shore would notice the hull of the vessel disappear first, followed by the mast, until only the top of the sail was visible before it vanished entirely. This phenomenon suggested that the ship was moving over a curve, rather than just shrinking into the distance on a flat surface. Imagine standing on a beach and watching a distant ship. Its bottom vanishing before its top was a clear sign to those who looked closely. Another piece of compelling evidence came from lunar eclipses. A lunar eclipse happens when the Earth passes directly between the Sun and the Moon, casting a shadow on the Moon. Medieval astronomers observed that the shadow cast by the Earth on the Moon during these eclipses was always curved, consistently forming a segment of a circle. The only shape that consistently casts a circular shadow, regardless of its orientation, is a sphere. This consistent circular shadow was a powerful visual confirmation of Earth's roundness. Furthermore, the stars visible in the night sky changed as one traveled north or south. Travelers journeying towards the equator would see new constellations rise above the horizon, while those that were high in the sky further north would sink closer to the horizon or disappear altogether. For instance, the pole star Polaris appears higher in the sky the further north an observer travels. If the Earth were flat, the same stars should be visible everywhere, just appearing smaller or dimmer. The change in the celestial panorama directly supported the idea of an observer moving across a curved surface. Many scholarly texts from the medieval period discuss the spherical Earth. Bede, an Anglo-Saxon monk writing in the 8th century, explicitly stated in his work The Reckoning of Time that the Earth was round. He described it as a globe, not just a circle, and explained that this roundness was the reason for the varying lengths of daylight and night across different parts of the world. In the Islamic world, scholars like al-Biruni, who lived in the 10th and 11th centuries, made remarkable calculations concerning the Earth's circumference. He described a method to measure the Earth's radius by observing the dip of the horizon from two different elevations, a complex geometrical approach that assumed a spherical Earth. His estimate for the Earth's circumference was very close to modern measurements, demonstrating a sophisticated understanding of Earth's geometry. These examples illustrate that the idea of a spherical Earth was not an isolated thought, but a widely accepted and studied concept within the medieval intellectual landscape. The widespread acceptance of a spherical Earth demonstrates that medieval astronomers, using careful observation and logical deduction, held surprisingly accurate beliefs about the fundamental shape of our world. Number 11. The length of the year. Concept of a year, the time it takes for the Earth to complete one orbit around the Sun, was a crucial piece of knowledge for medieval societies. It dictated planting seasons, harvest times, and the scheduling of religious festivals. Accurately determining the length of the solar year was not just an academic exercise. It had profound practical implications for survival and societal order. Medieval astronomers, particularly in the Islamic world and later in Europe, put immense effort into precisely measuring this duration. Their results were remarkably close to the actual length of the solar year we use today. The Julian calendar, established in ancient Rome and widely used throughout Europe during the medieval period, approximated the year as 365.25 days. This was a good starting point, but it was not perfectly accurate. The true length of a tropical year, the time from one vernal equinox to the next, is approximately 365.24219 days. The Julian calendar's slight overestimation of the year's length led to a slow drift, causing the calendar dates of seasons and astronomical events like the equinoxes to shift over centuries. For instance, the vernal equinox, which marks the beginning of spring, was meant to fall on March 21st, but over hundreds of years, it began to occur earlier and earlier in the calendar. Medieval astronomers were acutely aware of this drift. They meticulously tracked the movement of the sun against the background stars and recorded the precise moments of the equinoxes and solstices. Instruments like sundials, quadrants, and armillary spheres helped them determine the sun's position in the sky throughout the year. They would observe the length of shadows cast by gnomons, the vertical part of a sundial, at noon on specific days to mark the sun's highest and lowest points in the sky, corresponding to the solstices. Equal length of day and night marked the equinoxes, and these moments were carefully observed. In the Islamic world, astronomers made significant strides in refining the length of the year. Scholars like al-Battani, living in the 9th and 10th centuries, dedicated years to astronomical observations. Calculated the length of the tropical year to be 365 days, 5 hours, 48 minutes, and 24 seconds. This figure is incredibly close to the modern accepted value. His work, documented in his astronomical tables known as the Zij, demonstrated a high level of observational precision and mathematical skill. Another notable figure was Omar Khayyam, a Persian polymath of the 11th and 12th centuries. He led a group of astronomers who reformed the Persian calendar, creating the Yalali calendar. This calendar, introduced in 1079 AD, is considered one of the most accurate solar calendars ever devised, even more accurate than the Gregorian calendar for a period of time. Its accuracy stemmed from a sophisticated system of leap years, based on precise astronomical observations of the vernal equinox. The Sali calendar calculated the year to be 365.2421986 days, which is remarkably close to the true value. These efforts across different cultures highlight a shared commitment to empirical observation and mathematical rigor. Continuous tracking of the sun's position, the recording of equinoxes and solstices over generations, and the development of more precise instruments allowed medieval astronomers to progressively refine their understanding of the solar year. Their ability to measure the year with such precision long before telescopes and atomic clocks shows an impressive level of dedication and accuracy in their astronomical pursuits. The adjustments and refinements they proposed, like the efforts to reform the Julian calendar, eventually paved the way for the Gregorian calendar reform centuries later. Number 10. Eclipse prediction. The sight of an eclipse, whether of the sun or the moon, has always been a powerful and often awe-inspiring event. In medieval times, without a scientific understanding of their cause, eclipses could be viewed as omens or supernatural occurrences, sometimes inspiring fear or wonder. Yet, medieval astronomers, building on ancient knowledge and adding their own meticulous observations, developed sophisticated methods to predict these celestial events with remarkable accuracy. This ability to foresee eclipses was a testament to their deep understanding of the regular motions of the sun, moon, and earth. Key to predicting eclipses lies in understanding the cyclical nature of their occurrence. Eclipses do not happen randomly, they follow predictable patterns. One of the most important of these patterns is the Saros cycle. This cycle, known to ancient Babylonian astronomers and fully utilized by medieval scholars, describes a period of approximately 18 years, 11 days, and 8 hours after which the Sun, Earth, and Moon return to roughly the same relative positions, leading to a recurrence of similar eclipses. Medieval astronomers in both the Islamic world and Europe had access to and expanded upon these ancient records, compiling their own extensive tables in astronomical simjais, collections of astronomical tables that incorporated the Saros cycle. Astronomers in the Islamic Golden Age were particularly adept at eclipse prediction. Scholars like al-Battani, 9th-10th century, refined existing astronomical tables and made new observations to improve the accuracy of predictions. His zij included detailed calculations for lunar and solar eclipses, providing precise times and locations of visibility. He used complex mathematical models, building upon Ptolemy's work, but also correcting errors and adding his own precise observational data. Imagine the painstaking work involved, recording the exact time and appearance of hundreds of past eclipses, then analyzing this vast paitemate to uncover the underlying patterns. In Europe, while progress was sometimes slower than in the Islamic world, scholars also engaged in eclipse prediction. Monastic chronicles often recorded eclipses, and some scholars like Roger Bacon, 13th century, discussed astronomical tables and the prediction of celestial events. However, European astronomy was heavily influenced by translations of Arabic texts, which brought with them the advanced methods developed in the East. Astronomers would calculate the positions of the Sun and Moon along with the nodes of the Moon's orbit, the points where the Moon's path crosses the ecliptic, the Sun's apparent path. Eclipses can only occur when the Moon is near these nodes. The accuracy of these predictions was often quite high. For instance, historical records from medieval Baghdad mention scholars successfully predicting solar eclipses, allowing people to observe them without fear of surprise. Precise times of lunar eclipses were also predicted for religious purposes, such as determining the start and end of fasting periods in some cultures. The ability to predict eclipses not only showcased advanced mathematical and observational skills, but also allowed societies to prepare for these events, sometimes turning moments of potential apprehension into opportunities for scientific observation. The fact that medieval astronomers could reliably forecast these intricate celestial ballets, using only their intellect, careful observation, and sophisticated calculations, is a testament to their deep understanding of celestial mechanics. Number 9. Retrograde motion of planets. One of the most perplexing and fascinating phenomena observed in the night sky is the apparent backward motion of planets. Most of the time, planets move in a steady eastward direction against the background stars. However, at certain points in their cycles, they appear to slow down, stop, reverse direction, and move westward for a period, then slow down again, stop, and resume their eastward journey. This puzzling behavior is known as retrograde motion. Medieval astronomers accurately observed this retrograde motion, even though their explanation for it was complex and ultimately not how we understand it today. For an observer on Earth, planets like Mars, Jupiter, and Saturn exhibit this looping behavior. Imagine tracking Mars night after night against the fixed stars. For weeks or months, it moves consistently in one direction. Then, it seems to pause, drift backward for a while, and then resume its forward march. This observation was undeniable. Medieval astronomers, particularly those who meticulously charted the heavens, made detailed records of these planetary paths. They were keen observers, relying on the naked eye and instruments like armillary spheres to precisely mark the positions of these wandering stars over time. The accurate observation of retrograde motion presented a significant challenge to the prevailing geocentric model of the universe, which placed Earth at the center with all other celestial bodies orbiting it in perfect circles. If planets orbited Earth in simple circles, they should always move in the same direction. To account for the observed retrograde motion while maintaining the geocentric model and the philosophical idea of perfect circular motion, medieval astronomers adopted and refined the complex system of epicycles and deferents, primarily developed by Ptolemy in ancient times. A deferent was a large circle around the Earth, and an epicycle was a smaller circle whose center moved along the circumference of the deferent. The planet itself was said to move on the circumference of the epicycle. When the planet on its epicycle moved in the same direction as the epicycle's center on the deferent, the planet appeared to move forward. But when the planet on its epicycle moved in the opposite direction to the epicycle's center, it created the illusion of backward motion or retrograde motion, as seen from Earth. While this model was mathematically intricate, it was incredibly successful at predicting the observed positions of the planets, including their retrograde loops. Many medieval astronomers, especially in the Islamic world, devoted enormous effort to improving Ptolemy's models. Scholars at observatories like the Maraga Observatory in Persia, 13th century, and the Samarkand Observatory in Central Asia, 15th century, gathered vast amounts of observational data. They meticulously recorded the positions of planets over many years, creating sophisticated astronomical tables. These tables allowed them to calculate when and where retrograde motion would occur for each planet. Although the underlying explanation of epicycles was a geometric construct to fit observations rather than a physical reality, the observation of retrograde motion itself was accurate. Their ability to predict when and where these backwards movements would happen using their complex models is a testament to their observational rigor and mathematical ingenuity. They saw it, they charted it, and they predicted it. Number 8. Stellar catalogs and star mapping. Imagine looking up at the night sky and seeing thousands of stars, seemingly scattered randomly. How would you begin to make sense of them, to understand their positions, and to use them for navigation or timekeeping? Medieval astronomers took on this monumental task, creating detailed star catalogs and maps that meticulously documented the positions and brightness of countless stars. These efforts were surprisingly accurate and formed the backbone of astronomical knowledge for centuries, proving essential for scientific study and practical applications like sea travel. Tradition of star cataloging goes back to ancient times, with figures like Hipparchus and Ptolemy compiling significant lists. However, medieval astronomers did not just copy these older works. They rigorously reobserved the skies, corrected previous errors, and added new stars to the existing catalogs. This was a painstaking process, requiring immense patience and precision. They used instruments like large quadrants, armillary spheres, and eventually specialized instruments like the torquetum to measure the angular positions of stars in the celestial sphere. These measurements were then recorded in tables and diagrams. One of the most famous and comprehensive star catalogs from the medieval period was the Book of Fixed Stars, Kitab Suwar al-Kawakib al-Thabita, by Abdurrahman al-Sufi, a Persian astronomer of the 10th century. Al-Sufi's work was not just a list, it was an illustrated atlas. He described the constellations, provided magnitudes, a measure of brightness, for each star, and included detailed drawings of the constellations as perceived by Arab, Greek, and other traditions. For example, Al-Sufi identified the Andromeda galaxy, which he called a little cloud, nearly 1,000 years before telescopes allowed for its clearer observation by Europeans. He noted its position relative to stars in Andromeda and described its appearance. His catalog included more than 1,000 stars, meticulously listing their coordinates. Centuries later, in the 15th century, Ulugh Beg, a Timurid sultan and astronomer, established a grand observatory in Samarkand, Central Asia. Under his patronage, astronomers compiled the Zig-i-Sultani, a monumental astronomical table that included a star catalog with the positions of 1,018 stars. These star positions were determined with incredible accuracy, for the time often rivaling or even surpassing the precision of instruments available centuries later. The observatory's main instrument, a colossal Fakhri sextant, had a radius of over 36 meters, around 118 feet, allowing for extremely precise angular measurements. Precision of Ulugh measurements was so high that they were still referenced by astronomers hundreds of years later. These star maps and catalogs were not merely academic curiosities, they were vital tools for navigation, especially for maritime travel across vast oceans. Sailors relied on the positions of stars to determine their latitude and direction. Accurate star charts meant safer and more efficient voyages. For religious purposes, such as determining the correct direction of prayer, Qibla, in Islam, precise astronomical data was essential, and star catalogs provided the necessary coordinates. The existence of these detailed, accurate catalogs, compiled over centuries of diligent observation, shows the remarkable dedication of medieval astronomers to systematically charting the cosmos. They essentially created the first comprehensive roadmaps of the night sky, a foundational achievement for all subsequent astronomical exploration. Number 7. Tidal forces and the moon. The rhythmic ebb and flow of the ocean, known as tides, has always been a powerful and undeniable force of nature. For people living near coastlines, understanding tides was crucial for fishing, trade, and travel. While medieval astronomers did not have a full understanding of gravity as explained by Isaac Newton centuries later, they did observe and accurately correlate the tides with the phases and movements of the moon. This was a significant step towards understanding the moon's influence on Earth. The most striking observation was the daily cycle of tides. Observers noted that the sea level rose and fell twice a day, a cycle that generally coincided with the moon's apparent passage across the sky. The high tides occurred when the moon was overhead or on the opposite side of the Earth, and low tides occurred when the moon was at its quadrature, 90 degrees away. This daily synchronicity was too consistent to be a coincidence. People living along the coasts, such as those in Britain, witnessed this phenomenon regularly and passed down knowledge of its patterns. Beyond the daily cycle, medieval observers also noticed the correlation between the moon's phases and the strength of the tides. They recognized that the highest tides, known as spring tides, occurred around the times of the new moon and full moon. During these periods, the sun, earth, and moon are roughly aligned. The lowest tides, called neap tides, occurred when the moon was in its first and third quarter phases, meaning the moon was at a right angle to the sun relative to Earth. This consistent pattern of stronger and weaker tides linked directly to the lunar cycle provided further evidence of the moon's profound influence on Earth's waters. One of the earliest medieval scholars to explicitly discuss the moon's influence on tides was Bede, the Anglo-Saxon monk from the 8th century. In his work, The Reckoning of Time, he described in detail how the tides followed the moon. He noted that the tide arrived later each day, mirroring the moon's later rising time. He also explained the difference between spring and neap tides, attributing the former to the combined pull of the sun and moon when they were aligned. While he didn't use the term gravity, his description of the moon's drawing or attraction on the waters was a remarkably accurate conceptualization of the phenomenon. In the Islamic world, scholars like al-Biruni, 10th, 11th century, also discussed tides. He documented observations of the sea's behavior in different parts of the world and explored various theories about the cause of tides, including the influence of the moon. He even considered the idea of atmospheric tides, contemplating whether the moon could affect the air in a similar way to the water. While his full understanding of the underlying physics was not complete, his detailed observations and attempts to explain the cause demonstrate a sophisticated awareness of the lunar tidal connection. The medieval understanding of tides, though lacking the full theoretical framework of universal gravitation, was remarkably accurate in its observational findings. They charted the predictable patterns correctly, linked the moon's phases to the strength of the tides, and even described the daily lag in tidal timing. This practical knowledge, built from generations of careful observation along coastlines, allowed communities to live in harmony with the sea, utilizing its currents and predicting its ebbs and flows for navigation, fishing, and trade. The fact that they accurately discerned this complex relationship between a celestial body and terrestrial phenomena without modern scientific tools is a clear example of their observational prowess. Number 6. Celestial object regularity. The medieval night sky, unpolluted by city lights, offered a grand spectacle of order and predictability. For centuries, people looked up and saw that the stars, planets, sun, and moon moved in regular, unchanging patterns. This belief in the regularity of celestial objects, their predictable paths, and consistent motions was a cornerstone of medieval astronomy. It led to the idea of a cosmic clockwork, a universe governed by dependable laws, even if the precise nature of those laws was not fully understood. From the daily rising and setting of the sun and moon to the annual cycle of the seasons, the cosmos seemed to operate with perfect consistency. The stars appeared to rotate around a fixed point in the sky, maintaining their relative positions to each other. This unchanging backdrop of fixed stars provided a stable framework against which the wandering stars or planets could be observed. While planets exhibited more complex motions like retrograde loops, even these were understood to be predictable and recurrent, following an established order. Medieval astronomers meticulously tracked these regular motions. They developed calendars and almanacs based on the precise timing of celestial events. Predictability of the sun's path allowed them to determine solstices and equinoxes, crucial for agriculture and seasonal festivals. The moon's consistent phases from new to full and back again provided a natural timekeeping mechanism. Historical records from various observatories, particularly in the Islamic world, contain thousands of pages of observational data detailing the precise positions of celestial bodies over many years. These records were used to create astronomical tables that predicted future positions and events. The concept of celestial spheres was central to explaining this perceived regularity. It was believed that each celestial body was embedded in its own transparent nested sphere, and these spheres rotated, carrying their respective bodies across the sky. While the physical reality of these spheres is now known to be inaccurate, the model itself perfectly captured the observed regularity of motion. It explained why stars maintained their relative positions, why the sun followed a consistent annual path, and why planets moved in predictable, though complex, patterns. This philosophical framework reinforced the idea of an orderly and harmonious universe. Observatories like the one at Moraga in the 13th century or Samarkand in the 15th century were built specifically to enhance the precision of these observations. Astronomers at these institutions used large instruments like Miro quadrants and armillary spheres to measure the angular positions of celestial objects with unprecedented accuracy. The results of their observations consistently confirmed the predictable nature of the cosmos. For instance, the regular intervals between lunar eclipses, as captured by the Saros cycle, provided powerful evidence of consistent celestial mechanics. The belief in celestial regularity meant that medieval astronomers viewed the universe as something that could be studied, understood, and even predicted. They saw the cosmos as a grand, intricate machine, operating according to fixed rules. This belief laid the groundwork for future scientific inquiry, fostering a mindset where patterns were sought, data was collected, and models were developed to explain the observed phenomena. The regular behavior of the celestial bodies was not just a theoretical concept. It was a directly observed reality that shaped their entire worldview and fueled their astronomical pursuits. Number 5. Development of astronomical instruments. Without the sophisticated telescopes and computer models of today, How did medieval astronomers make their remarkably accurate observations? The answer lies in their ingenuity and craftsmanship in developing a range of advanced astronomical instruments. These tools, often masterpieces of engineering and artistry, allowed them to measure angles, track positions, and understand the movements of celestial bodies with impressive precision. The creation and refinement of these instruments represented a significant technological advancement and were crucial for the progress of medieval astronomy. Perhaps the most iconic medieval astronomical instrument is the astrolabe, originating in ancient Greece, but significantly refined and popularized in the Islamic world. The astrolabe was a versatile instrument used for a multitude of purposes. It could determine the time of day or night, calculate the time of sunrise and sunset, find the positions of stars and planets, and even aid in navigation. Typical astrolabe consisted of a flat disk with a map of the stars and a rotating retit, a framework representing the ecliptic and stars that could be aligned with the sky. By sighting a star through a movable rule, an astronomer could read its position on the engraved scales. Scholars like Muhammad al-Fazari, 8th century, are credited with early developments of the astrolabe in the Islamic world, and later master craftsmen created highly precise and beautiful instruments. These tools were widespread and used in both the Islamic East and the Latin West. Another fundamental instrument was the quadrant. As its name suggests, a quadrant is a quarter of a circle, typically made of wood or metal, with a sighting mechanism and a graduated arc. It was used to measure angles, particularly the altitude of celestial bodies, their height above the horizon. Larger quadrants were built into observatories, fixed to a wall, mural quadrants, allowing for extremely precise measurements of stars and the sun as they crossed the meridian. The Samarkand Observatory under Ulu Beg housed an enormous Fakhri sextant. A sextant is similar to a quadrant but measures 60 degrees, a giant arc built into the ground which allowed for unparalleled accuracy in measuring stellar positions. Armillary spheres were also important instruments. These were skeletal models of the celestial sphere, made of rings representing the equator, ecliptic, and meridians. By adjusting the rings and sighting through specific points, astronomers could visualize and measure the positions of celestial bodies in 3 dimensions. They were used for teaching, demonstrating celestial mechanics, and for taking some measurements. The torquetum, a unique instrument developed in the 12th century, particularly in the Islamic world and later in Europe, was designed to convert celestial coordinates between different systems, e.g. from equatorial to ecliptic coordinates. It was a complex mechanical device, reflecting a sophisticated understanding of spherical trigonometry and instrument design. Craftsmanship involved in creating these instruments was extraordinary. They were often made from brass, copper, or other durable metals, engraved with precise markings and scales. The accuracy of the measurements taken with these instruments depended entirely on the precision of their construction. Observatories were established to house these large instruments and to provide dedicated spaces for continuous observation. The astronomers who used them were not just theoreticians. They were also skilled observationalists and often proficient instrument makers themselves. The advancements in instrument design and construction during the medieval period directly enabled the accurate observations and calculations that define medieval astronomy. These tools were the eyes and hands of medieval astronomers, allowing them to unveil the secrets of the cosmos. Number 4. Understanding of celestial spheres. Medieval astronomers believed in a model of the universe based on a series of nested, transparent spheres, with the Earth at the center. This model, often referred to as the celestial spheres or the Ptolemaic system after the ancient Greek astronomer Claudius Ptolemy, was a dominant cosmological framework throughout the medieval period. While the idea of physical crystal spheres is now considered inaccurate, This model was surprisingly effective as a conceptual tool for organizing observed astronomical phenomena and predicting celestial movements, provided a coherent framework for understanding the order of the cosmos. In this model, the Earth was stationary at the center of the universe. Around the Earth, concentric spheres carried the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn in that order. Beyond the sphere of Saturn was the sphere of the fixed stars, which carried all the visible stars that appeared to maintain their relative positions. Finally, there was often an outermost sphere, the primum mobile, which imparted motion to all the inner spheres. Each sphere rotated, carrying its celestial body with it, accounting for the daily motion of the stars and the monthly or annual paths of the planets. This model was philosophically appealing. It incorporated the idea of perfect circular motion, which was seen as the most ideal form of motion in the heavens. It also provided a clear hierarchy and order to the universe. For medieval scholars, the universe was not chaotic, but a divinely ordered creation, and the celestial spheres provided a rational, elegant explanation for its apparent regularity. Despite its ultimate physical inaccuracy, the model of celestial spheres was incredibly useful for descriptive and predictive purposes. It provided a systematic way to describe the observed paths of celestial bodies. For instance, the sphere of the Sun explained its apparent annual movement through the constellations of the zodiac. The sphere of the Moon explained its monthly cycle. The fixed stars on their outermost sphere accounted for their unchanging patterns in the night sky as they rotated around the Earth each day. To account for the observed complexities, such as the retrograde motion of planets, the simple spheres were augmented with more complex geometrical devices like epicycles and deferents, as discussed earlier. These mathematical additions were superimposed on the basic spherical model, allowing it to predict the observed positions of planets with considerable accuracy. While the physical interpretation of these epicycles, as actual wheels within wheels, is no longer accepted, their mathematical utility in predicting planetary positions was undeniable. Medieval astronomers, particularly in the Islamic world, spent centuries refining these Ptolemaic models, developing more precise calculations for the sizes and speeds of these hypothetical spheres and their epicycles. Astronomical instruments like the armillary sphere were physical representations of this spherical model, helping astronomers visualize and calculate celestial coordinates. Students could manipulate the rings of an armillary sphere to understand how the planets and stars were thought to move. Continued use and refinement of the celestial sphere model for over 1400 years, from Ptolemy to the Renaissance, demonstrates its conceptual power. It offered a comprehensive, albeit complex, framework that allowed medieval astronomers to organize their observations, make predictions, and understand the general order of the cosmos, providing a working model that captured the observed regularity of the heavens surprisingly well, even if the underlying physics were misunderstood. Number 3. The geocentric model. Throughout the medieval period, the prevailing view of the universe was the geocentric model, meaning Earth was believed to be at the absolute center of the cosmos. All other celestial bodies, including the Sun, Moon, planets, and stars, were thought to revolve around a stationary Earth. This belief was deeply ingrained in both scientific thought and philosophical understanding across various cultures from Europe to the Islamic world. While we now know this model to be incorrect, it was a perfectly logical conclusion based on direct, everyday observation and was supported by seemingly obvious evidence. From an observer's perspective on Earth, the geocentric model simply made sense. Every day, the sun visibly rises in the east, moves across the sky, and sets in the west. At night, the moon and stars also appear to circle around the Earth. There was no apparent sensation of Earth's motion. It felt solid and stationary. If the Earth were truly moving, why would objects thrown into the air fall straight down instead of being left behind? Why did a constant wind not blow across its surface? These common sense observations seem to confirm Earth's central and immobile position. The geocentric model was primarily based on the works of ancient Greek philosophers, like Aristotle, and astronomers like Ptolemy. Aristotle, in the 4th century BC, proposed a philosophical system where Earth was composed of 4 elements, earth, water, air, fire, that naturally moved towards the center, while the heavens were made of a perfect, unchanging 5th element called aether, which moved in perfect circles. This neatly placed Earth at the center. Ptolemy, in the 2nd century AD, developed a comprehensive mathematical and geometric model in his monumental work, the Almagest, which described the movements of the planets Sun and Moon around a central Earth. This model, with its complex system of epicycles, deferents, and equants, was remarkably accurate for predicting celestial positions for centuries. Medieval scholars in Europe and the Islamic world inherited and largely adopted Ptolemy's geocentric system. They painstakingly translated, studied, and commented on the Almagest. In the Islamic world, observatories were established, and astronomers like al-Battani and Nasir al-Din al-Tusi refined Ptolemy's parameters and sometimes critiqued aspects of his model, but they still operated within the geocentric framework. They improved the accuracy of planetary predictions but did not challenge the fundamental premise of Earth's centrality. Similarly, in medieval European universities, the Ptolemaic system was taught as the authoritative view of the cosmos. The geocentric model allowed for the creation of functional calendars, accurate navigation, and reliable predictions of celestial events like eclipses. Its predictive power, despite its incorrect underlying assumption, reinforced its validity for centuries. It was not until the 16th century, with the work of Nicolaus Copernicus and later Johannes Kepler and Galileo Galilei, that a new, heliocentric, sun-centered model began to gain acceptance, challenging the long-held geocentric view. The shift from a geocentric to a heliocentric universe represented a profound paradigm shift. But for nearly 1,400 years, the geocentric model served as a robust and widely accepted framework for understanding the cosmos, based on what seemed to be obvious observational evidence. Number 2. Perfect circular orbits. A fundamental belief in medieval astronomy, inherited from ancient Greek philosophy, was that all celestial bodies moved in perfect circular orbits. This idea stemmed from the philosophical conviction that the circle was the most perfect and divine geometric shape. Therefore, it was reasoned that the heavens, being perfect and eternal, must exhibit motion only in circles. This belief deeply influenced how medieval astronomers constructed their models of the universe, forcing them to devise increasingly complex mathematical constructs to reconcile this ideal with the observed, sometimes erratic motions of planets. This belief in perfect circular motion can be traced back to Plato and Aristotle. Plato, in his Timaeus, described the cosmos as being ordered according to perfect geometric forms, with circles being paramount. Aristotle further developed this, proposing that the heavens were made of an incorruptible 5th element aether, and its natural motion was uniform circular motion. This idea became deeply entrenched in the scholastic tradition of medieval Europe, and was also influential in the Islamic world. The problem, however, was that the observed paths of planets, as seen from Earth, were not simple circles. As previously discussed, planets exhibit retrograde motion, appearing to move backward for a period. Their speeds also appear to vary. If planets were simply moving in perfect circles around a central Earth, these observations would not fit. To reconcile the observed complexities with the philosophical ideal of perfect circular motion, medieval astronomers adopted and elaborated on Ptolemy's intricate system of epicycles, deferents, and equants. A deferent was a large circle around the Earth, and an epicycle was a smaller circle whose center moved along the circumference of the deferent. The planet itself was said to move on the circumference of the epicycle. By adjusting the sizes and speeds of these circles and the position of their centers, medieval astronomers could create models that accurately predicted the observed planetary positions, including the apparent speeding up, slowing down, and retrograde loops. For example, a planet moving on an epicycle that was itself moving on a deferent could trace out a complex, yet seemingly perfect, path that included retrograde motion, all while remaining within the philosophical confines of circular motion. Later, Ptolemy introduced another concept, the equant, to account for the observed variations in a planet's orbital speed. This meant that the center of the deferent was not always the center of uniform motion, but rather the angular speed was uniform when viewed from a point called the equant, which was offset from the center. This introduced a deviation from pure uniform circular motion, but was still an attempt to preserve the idea of uniform motion around a central point. Despite the mathematical success of these models in predicting planetary positions, the belief in perfect circular orbits led to increasing complexity. The models became highly intricate, requiring multiple layers of circles to describe the movement of just one planet. This complexity, while brilliant in its mathematical ingenuity, hinted at the underlying tension between philosophical ideals and observational reality. It was not until Johannes Kepler, in the early 17th century, demonstrated that planets move in elliptical orbits, not perfect circles, that this long-held belief was finally overturned. Transition from circles to ellipses greatly simplified the description of planetary motion and was a profound shift in astronomical understanding. But for centuries, the elegant ideal of the circle shaped the astronomical worldview. Number 1. Celestial bodies as perfect and unchanging. Deeply held belief throughout the medieval period, stemming from ancient Greek philosophy, was that celestial bodies were perfect, immutable, and unchanging. Unlike the imperfect, changing Earth, the heavens were considered to be eternal and free from corruption or alteration. This concept heavily influenced astronomical thought and how observed phenomena were interpreted, sometimes leading to misinterpretations or dismissals of events that contradicted this view. This idea originated with Aristotle, who posited that the terrestrial realm, Earth and its immediate vicinity, was made of 4 elements: earth, water, air, fire, and was subject to generation, corruption, and change. In contrast, the celestial realm, from the moon outwards, was composed of a 5th, perfect, and incorruptible element, called aether. This aether was believed to be eternal and unchangeable, moving in perfect circles. Therefore, the sun, moon, planets, and stars were seen as flawless, unchanging entities, always following their predetermined paths, without any new phenomena appearing or existing ones fading away. This belief had significant implications for how medieval astronomers viewed any unusual celestial event. For example, comets were often considered atmospheric phenomena below the sphere of the moon, rather than celestial bodies. Their transient nature and irregular paths were seen as evidence that they could not be part of the perfect, unchanging heavens. Similarly, the appearance of a new star, a supernova, posed a challenge to this doctrine. While such events were rare, they did occur. The most famous example from the medieval period was the supernova of 1054 AD, which was bright enough to be seen in daylight for weeks and was recorded by Chinese and Arab astronomers. How were these events interpreted within the framework of immutable heavens? Sometimes they were seen as temporary atmospheric phenomena, or as imperfections in the terrestrial sphere that somehow extended into the celestial. In Europe, the prevailing Aristotelian view often led to the dismissal of new stars as sublunar events, meaning they were thought to be within Earth's atmosphere rather than among the fixed stars. This was partly because directly observing change in the seemingly unchanging fixed stars would contradict a core philosophical belief. However, in the Islamic world, where observational astronomy was highly developed, scholars meticulously recorded these events, even if they struggled to reconcile them fully with the Aristotelian perfect heavens. They were simply observed facts. The concept of perfect and unchanging celestial bodies also meant that the positions and brightness of stars were assumed to be constant over long periods. While medieval astronomers meticulously catalogued stars and noted their brightness, the idea that a star might brighten dramatically, like a supernova, or even change its fundamental nature was outside the accepted cosmological framework. This contrasted sharply with the changeable nature of the Earth, which experienced seasons, births, deaths, and decay. This belief in celestial perfection was deeply intertwined with theological views in both Christianity and Islam, where the heavens were seen as a divine creation, reflecting divine order and perfection. Any deviation from this perfect order could be philosophically troubling. It was only much later, with the observations of Tycho Brahe's supernova in 1572 and Galileo Galilei's telescopic observations of sunspots and lunar craters in the early 17th century, that the idea of unchanging and perfect celestial bodies was seriously challenged and ultimately disproved. These later observations revealed a dynamic and sometimes violent universe, very different from the serene and immutable cosmos envisioned in the medieval period.